When we do our testing, the type of representation we get, there are different test modes that can represent our flaws and display them to us in different ways. And so the four main modes are referred to as A, B, C, and D scan. We're going to be just doing A scan. A scan is what I described with the graph where you have intensity or amplitude along the y-axis, excuse me, vertically, and then time, which is converted to distance because we figure out what the velocity of sound is, along the x-axis. And so it gives us, those are those pulses and peaks. B scan is kind of a side projection of the part. It's still a limited, kind of what I would call limited two-dimensional. It can tell you, kind of how far things are. C scan gives you probe echoes in relation to the probe position on a true 2D, kind of if you're looking down the same direction the probe is transmitting. And then D scan is similar to 3, but we can do time of flight and depth to give us a 3D visualization of the object. So what do these look like? Here is that A scan, as I mentioned. Probe intensity or sound intensity, amplitude is on the y-axis. And then the distance, which is time times the speed of sound in the material, is shown across the x-axis. And so what you're getting here is with this transducer, the initial pulse right here is where that sound is first entering, and you get an echo right off that surface. And then that's also part of that near field, so you really can't find anything in that area. You have your back wall echo right here off the back surface echo or back wall echo. And then here where there's a crack, it's also going to show an echo closer to the face of the probe. A B scan is similar, but now instead of the signal strength and the distance, now we have the distance on the Y scale. And then what it's saying by scan distance here, time depth, scan distance is the physical movement of the probe across the part. Okay? And so what you have to have is, in this case, if you're just holding this transducer, the tester has no idea where you've moved your probe. But if we're doing a B scan, we have to provide some kind of information to our tester about where the probe is located. And so what we put is, in addition to our probe, we put a little wheel type thing on the side of it. That's called a resolver, that as we move the probe, it turns the little wheel. It's like one of those little distance measuring wheels you use. I don't know if anyone's used those. You roll the wheel and it counts up how far you've gone. It does the same basic thing to tell the scanner how far you move, but it only does it in a linear direction. So if you move your probe in a linear direction, it can tell you, when you're to the left here, you're getting this back wall echo, that's A. And then as you move over, you can see there's a back wall echo between A and B and between B and C and after C. These are these lines shown here at the very bottom. They're kind of hard to see on the B scan. But then as you go over the cracks, it gives you an indication at B and an indication at C that shows you kind of their relative depths, how far they are compared to the face of the probe. So this can be done with a single probe with a resolver wheel. The other thing you can have is a line of coils, an array probe where it's just a single line, and it sends a pulse all at once, and it kind of looks at when all the returns are across that line, that array of probes. It's a very simple array type probe. So the next thing we can do then is, that was our B scan. We can take a similar thing and do what's called a C scan. And it's going to look similar to a B scan, except now we're going to, our resolver, instead of just being single direction in a line, we would do a two-position resolver. So it can see where the probe is in a two-dimensional plane, and it records what the intensity is of the pulses in the different areas, different locations on that plane. And that can be done with a pair of resolvers, an X resolver and a Y resolver, two little wheels set 90 degrees from each other. or it can be done if you have a 2D array, basically a block of probes set up in a grid where you set it on a part and it kind of maps what the intensity is at different areas that that probe is covering. And then, so an indication of a C-scan looks something like this. So this one, the probe would be, this is with a dual resolver probe. It can tell the tester, you know, how far you've moved it up and how far to the right and how far you came back and how far to the right and how far you moved it up and how far to the right. And it creates a map that looks like this where, you know, oftentimes they're now color coded to give you, you know, basically different colors tell you different depths. And the scale would be over here, how deep each of those colors are. Okay. If we take that and we render it into a three-dimensional view, tip it up into the side where we can see it, then we end up with a D scan. And we can actually start to look at the topography of our probe or of our part. So not just looking at what the intensity is, but actually mapping the intensity onto that third dimension. And you can see this actually is a D scan with a C scan overlay. So not only does it show the true depth, but then it color codes the depth as well. You know, if you took this and made it flat, that would be a C scan. So it's a D scan with a C scan overlay, a colored overlay that also gives you an idea of what the intensity is. And again, that can be done with a array type probe, or it can be done with a probe with a dual resolver system on it. So. I'm going to go ahead and stop there for today.